For decades, computer science relied on symbolic logic. Programmers wrote explicit instructions. If X happens, then execute Y. Today, the industry has added a different layer. We now use deep learning, processing massive volumes of unstructured data to generate text, images, and code. Instead of writing code for every specific scenario, engineers train these systems on large datasets. The machine is left to identify patterns within that data without being told exactly what to look for. Large language models, or LLMs, use this method to predict the next word in a sequence. They identify linguistic and structural relationships by calculating how often certain concepts appear near each other in their training library. This scaling mechanism links the model's performance directly to the quality of its training data. If the data contains specific human biases, the model's mathematical weights will record and replicate those associations. To manage these systems, we have to look past the user interface and understand the exact mechanical vulnerabilities within the underlying architecture. Many users assume that because these systems run on silicon and math, the outputs are inherently neutral. This perspective was built on early computing milestones. When a computer defeated chess world champion Garry Kasparov in 1997, it proved that machines could outcalculate the human mind in an environment governed by fixed absolute rules. Modern LLMs operate differently. They do not calculate absolute truth. They calculate the probability of a sequence. They provide the most likely answer based on the patterns they have seen before. We are going to map the specific architectural mechanics of these models. By doing so, we can locate the exact points where ethical failures enter the workflow. Identifying these probabilistic risks is a requirement for any organization deploying AI in high-stakes environments. This is a neural network. Information enters an input layer, passes through hidden layers, and terminates at an output layer. At each node, a mathematical weight is applied, determining the signal's strength. Through repetition, it adjusts these weights, strengthening pathways for accurate predictions. This simple architecture is effective for identifying isolated objects, but it struggles with human language, where the meaning of a word is often determined by a sentence from several pages ago. Because standard networks fail to maintain this long-range context, researchers developed a different architecture to handle complex variables. The transformer architecture was designed specifically to address the problem of context. Its core mechanism is called self-attention. It mathematically weighs the importance of every data point against all others in a sequence, allowing the model to see how a word at the end of a document relates to a word at the beginning. This happens automatically. The model discovers these contextual relationships without a human engineer needing to label the connections manually. When applied to millions of gigabytes of text, this mechanism tracks billions of individual relationships simultaneously. The result is a high-dimensional map of human language and logic, capable of predicting incredibly complex sequences. However, because the self-attention mechanism derives its logic from those associations, its foundational weights are dictated by the implicit biases within the raw training data.
If the training data contains unrepresentative samples or historical prejudices, the model records those errors as objective patterns. Self-attention vectors distort toward these biased clusters. The model learns that certain concepts belong together based on the flawed dataset. This creates the black box. As billions of weighted layers build, the exact reasoning path becomes entirely hidden from its creators. Once a biased weight is integrated into this dense architecture, it becomes mathematically difficult to isolate or remove it without rebuilding the entire system. When these opaque models are used for critical decisions, architectural flaws become real-world failures. In healthcare, models trained on narrow demographic data develop a skewed baseline for medical conditions. This skew results in less accurate treatment recommendations for patients from marginalized groups who were underrepresented in the training set. In the financial sector, AI credit scoring models ingest decades of lending history, often learning to use proxy variables for neighborhoods. These models then mathematically penalize applicants from certain backgrounds, denying them access to capital based on historical patterns rather than current creditworthiness. Predictive policing tools in criminal justice absorb historical arrest data, which often includes existing racial biases. These systems then produce automated risk assessments that reinforce those legal disparities, hiding them under the appearance of mathematical neutrality. Algorithmic discrimination is a mathematical outcome of training a probabilistic model on flawed historical data. Reliable deployment requires acknowledging that these models will reproduce the flaws of their training data. We must design for that outcome. A white paper in the World Journal of Advanced Research and Reviews argues that AI governance must be part of the initial engineering design. It treats transparency as a technical countermeasure, requiring systems that can explain their reasoning to a human operator. It mandates fairness, the technical auditing and balancing of data before it is ever used to train the self-attention mechanism. The framework also emphasizes privacy and security, ensuring that the processing of large datasets does not expose sensitive user information. Finally, it establishes accountability by hard-coding human override capabilities into every autonomous workflow. These principles serve as technical requirements for maintaining predictable performance across any large-scale deployment. Organizations can implement 3 specific strategies. First, inclusive development teams can identify dataset blind spots before the training process begins. Second, implementing continuous auditing identifies mathematical tract and bias as the model processes new information in live environments. Third, establishing accountability frameworks ensures that a human in the loop can review and override automated decisions. Regulatory bodies are already codifying these strategies into law, as seen with the European Union's recent efforts to govern high-stakes AI use. To trust these tools in critical industries, we must shift from building opaque probability engines to engineering verifiable systems. The success of an AI system depends on its technical accuracy and the transparency and equity of its real-world results.